Hey guys, welcome to Code Decode. In this video, we will be looking into microservices trade-off interview questions. And trade-off is, trust me, very important to understand when it comes to tricky and twisted interviews. So most of the time, they would ask you, why would you choose microservice over monolithic? So you should answer in such a way that I would choose microservice only when the system has enough scale, team complexity, or independent business domains that a monolithic stack becomes a bottleneck. The main reason why I would choose microservice over monolith is because I want to do some independent deployments so that if the payment changes, I should not change order service or pay inventory service. I should be able to scale independently so that during a sale time in e-commerce system, the orders or the product catalog is scaled on higher pods and payments are at the lower pods so that I can scale the product catalog surfing independently instead of scaling the whole application. Third is team ownership. Different teams can own different capabilities to reduce the coordination. Also, to have the fault tolerance, if the recommendation service goes down, I don't necessarily want an entire application to be down. So this is fault tolerant so that only one part of the application is affected. And fifth, I want technology independence so that I can create the payment service in some other language like Golang or something, and I can have the product catalog service in Python or something. So different services potentially use different technologies and different databases. That is where I want to modify and build all these applications as microservice applications. But there is always a trade-off. Whenever I choose microservice, I would have to face the network partitions, the distributed transactions, eventual consistency issues, the complexity increases. The observability complexity also increases. Discovery becomes difficult. Circuit breaker is what I have to implement. Exponential retries is what I have to do, and I will have an operational cost. So I would not choose microservice simply because application is growing. But I would choose microservice when I need independent deployment, independent scaling, clear ownership, and team autonomy. But I would not introduce them automatically because they also introduce distributed complexity. If those benefits don't justify the complexity, I would prefer monolith one. So there's always a trade-off. If I want these many independent stuff, then there's a trade-off that I will have the distributed system complexity. So you have to decide which trade-off you want to take up. The second is when a monolith application is actually better than a microservice application. So this might be a trick question around when you answer that this is when I will choose monolith or microservice. The next question would be when your monolith is much better than microservice. So monolith is often better when system is small, handled by a small team, still evolving, not requiring independent deployments or scalability, and it is heavily transactional and asset property is very important. In that situation, I will still stick with our monolith application. Now, if I create order service, payment service, inventory service, user service, notice service, I will have more problems than solutions. Now I would need discovery, I would need gateway, I would need Kafka, I would need distributed tracing, I would need centralized logging, I need CI/CD, I need circuit breaker, I need retry exponential stuffs and distributed transaction. And for a system that I don't need them, I will not use microservice, I will stick with monolith one. Another very important use case when you can still stick with monolith is to have the strong asset consistency across several pieces of data. That is where I will still stick with @ transaction and will not use microservice at all. So a monolith is better when system is small, team is small, scaling is required, strong transactional asset property is required. I will prefer monolith rather than the microservice. Hey guys, so recently we have launched a very new course on Udemy, that is Spring Security 7. So now we have total of 2 courses, one on the Spring Security, second on the full stack application with all the deployment, pipelines, CI/CD, AWS Cloud, Kubernetes, everything. In Spring Security, we have covered authentication, authorization, filter chains, CRAN types, JWTs, OIDCs, SSO, CSRF, CORS, and very important, we have created here also a full stack project with a front end, back end, and security is implemented using Auth0 and Keycloak. Both of those authorization servers we have defined and created an end-to-end POC in this course. And the next course was on a full stack application where you understand microservices, Angular, JUnits, Docker, Kubernetes, AWS, EKS, RDS, Mongo Atlas, Jenkins, CI/CD, Argo CD, everything. So this makes a complete end-to-end project with front-end, back-end, and security implemented, deployed on the cloud also. Links of both of these courses will be given in the description below. Also, we will try to give some free coupons. Just let us know in the comment section for which course you would need the coupons. We will try to avail the coupons for the courses for free in the next month. Just for a small request, please leave your genuine, honest comments on these courses. That will help us create more such free courses or discounted courses for you guys. Should every microservice has its own database? Ideally, each microservice should have its own data. So order service should have order database, payment service should have payment database, inventory should have inventory database. And this is important because database ownership should follow the service ownership also. Why? Because suppose order directly access the payment table, now payment does not really own its data. Now order becomes coupled to payment, and if payment changes, order breaks. So better approaches make them completely segregated, have their own databases, do not interact with each other's database but interact through each other through a REST or Kafka or synchronous or asynchronous communication. But does every service really need to have a separate database? Answer is no. This is an important point. Suppose you have the same Postgres cluster, you can have a DB schema for order, a DB schema for payment, a DB schema for inventory, while still maintaining the logical ownership. Later, you can move them to separate database once your system grows. So I would prefer database per service because it enforces ownership, it reduces coupling, but database per service does not necessarily mean a complete separate database server. We can start with separate schema and separate them when isolation or scaling is justified. Now, how would you choose between strong consistency and eventual consistency? And this is a very important question. After a write is succeeded, every succeeded and subsequent reads would not see a dirty value. That is strong consistency. For example, you transferred 1000 from account A to account B. Now, in a banking system, strong consistency is needed because you don't want another system to temporarily see the old balance and allow another withdrawal. So financial operations often require very strong consistency for critical transactions. While when it comes to eventual consistency, that means temporarily delay is fine and temporary dirty reads and writes are fine. So different services may temporarily have different states, but eventually they converge. What do I really mean by that? So if you say order service, you will have order created and then there is a search service. So after a few seconds, you will see whether order exists or order is, but in the search index, when you see list of all orders, you will see order is not yet visible. Even though you have placed an order, because it is an eventual consistency, because your search service is a separate microservice and your order microservice is a separate microservice. So when you create an order, it is created in order database, but it takes time to sync in a search database. So your order DB will be the write DB and your search service will be a read service. So you placed an order, but when you see all your order history and list, it might take some time to reflect the recent order because it is not yet synced because it is done through async communication through Kafka. So this is usually acceptable when it comes to microservice architecture. So when would you choose a strong consistency and when will you choose an eventual consistency? So use the strong consistency when stale or dirty data read is a very serious problem. For example, financial transactions, account balances, unique constraint, critical transactions, those are very critical business requirements. So you do not prefer eventual consistency in those situations. Now, when will you choose eventual consistency? So when temporary stale data is acceptable, where search indexes can still show the dirty read, that is where you can go for microservice architecture with eventual consistency. You can have notifications a bit delayed, you can have emails a bit delayed, you can have analytics a bit delayed, you can have recommendations and reporting a bit delayed. So I choose consistency based on business requirement. This is a very important interview statement. So if your business requirement is similar to a banking system, that is where you would need a strong consistency. Like financial losses might happen, invalid business status completely not possible, then that is where you will use a strong consistency. But if a temporary staleness is acceptable, for example, a temporary email delay, or when you place an order but your order history shows it is not yet reflected, then it is fine. Then you can have eventual consistency there. So where you want scalability, loose coupling and stateless is somewhat acceptable to a threshold, then eventual consistency is much better than strong consistency. So you always have a trade-off, and this is why I say trade-offs are very important, because it tells you how to choose between a situation A and situation B, and you should always know a trade-off of each and every choice you make. Now suppose there is a REST call versus a Kafka event. When would you choose what? So you would choose REST when caller needs immediate response. For example, your order service is waiting for the payment service and payment service is waiting for the payment response. Now before the order service makes sure that your order is accepted or failed, it has to know the payment response. So this is where you can use REST API or the synchronous communication and strong consistency. While when it comes to Kafka, when communications can be completely asynchronous, that is where you don't want tight coupling or you don't want to wait for it. That is where you can go for asynchronous communications. So you will use REST for synchronous and Kafka for async communications. For example, you have created an order, now you have to send the email notification that can go through Kafka. Advantages of REST is it is simple, it is immediate response, it is request response model, and it is synchronous communication. But the disadvantages, it is temporal coupling. Service A has to wait for service B. Then you have network dependency, you have downstream failure effects, and latency propagates. When it comes to Kafka, advantage is loose coupling, asynchronous processing, multiple consumers can listen to and have the replay capability. But the disadvantage is eventual consistency. Now, whenever it comes to asynchronous communication, whenever they ask for you for the trade-off, say it's eventual consistency, you will have a stale data reads for some time until the complete sync doesn't happen in asynchronous way. So more operational complexity, duplicate message can happen, ordering becomes a problem and hard to debug. So I would use REST when I need immediate response or synchronous validations. I will use Kafka when I want asynchronous communication with multiple consumers needing the event. This is also very important stuff. You cannot wait for 10 different things at simultaneous parallel response through REST. REST is usually one-to-one communication, but when you want one-to-many communications, you can go for Kafka. So when I want to decouple a service, I will use Kafka. I would not replace every REST call with Kafka because it would unnecessarily add complexity for a simple request response interactions. Now, if Kafka delivers a message twice, how would you handle it? This is an idempotency question. So Kafka consumer should generally be designed to assume that a message may be processed more than once. Because you have a Kafka producer, you have a Kafka consumer. Now there can be a chance that Kafka consumer reads the message twice. Now suppose there is a payment complete, event ID is 123. The consumer receives it, process payment, update payment. Then consumer crash before committing the offset. We have already seen in Kafka video that if you commit an offset, then only you would see that order is processed or the event is processed. If you don't commit, then you will get the message or delivered twice. It can happen twice, thrice until you don't mark the offset. So Kafka may deliver this event ID again. And if we blindly process it, you will have two times the payment received. So solution is maintain a processing event ID. Now when the message arrives, check is it already processed. If yes, ignore, otherwise store the event ID in database and process it. So this is how you make sure your idempotency is there. Ideally, business operations and recording the event ID should happen atomically. For example, you check the event ID, you update the business state, you insert the event ID and commit. So I design the consumer to be idempotent. I give each event a unique event ID and persist those IDs in some database or some persistent state and use that ID as idempotency key. So when the same event arrives again, I detect that with my persisted event ID and I don't process it again, which prevents the duplicate processing and have the better business operations. Now, why can't we use a normal database transaction across microservices? Because a normal transaction is usually scoped to only one database. So suppose there is an order service with order DB, payment service with payment DB. Now, even if I want to do begin transaction, create order and create the payment, a normal Spring would have done with @transactional. But it does not magically make two independent databases one asset transaction. Now with microservice, you are into a problem called as distributed systems, and distributed system have its own problem of distributed transaction. So that is why even if you say @transactional and call another microservice, it will not be transactional. You cannot make two microservice transactional. The only thing you can make is an attempt to insert, delete or CRUD in a database transactional, but you cannot make two microservice calls transactional. So if you want to have a proper distributed transaction, we can use 2PC, or if you want strong consistency, use 2PC. If you want eventual consistency, use Saga. So when would you use 2PC? When coordination overhead is there, latency is a problem, blocking is a problem. When will you not use 2PC? When eventual consistency is fine, because 2PC introduces a lot of overhead, latency, blocking, operational complexity and concerns. And when will you prefer Saga with eventual consistency? When distributed asset transactions are not needed. So a normal database transaction provides atomicity within a transactional resource. Once the data is distributed across independent databases, we need to distribute transaction coordination also. Too much of theory. Understand the fact that a single database, you can have a transaction. But two different databases, that too communicating with two different microservices, you cannot have the traditional asset transaction there. The way to manage the transactions in such distributed system is either through 2PC or Saga. 2PC is when you need strong consistency, Saga is when you need eventual consistency. And now when will you choose Saga versus 2PC? So when you need strong consistency, use 2PC. How would it work? There is a coordinator. There are 3 DBs. So phase 1 says prepare. So all of them prepare for commit. Phase 2 says commit. All of them commit together. So all participants agree before committing. Advantages, strong consistency, and disadvantages is expensive. There is a coordination overhead. This is blocking. This reduces the availability and tight coupling. While when it comes to Saga, they are local transactions. So if the create event is created, then charge payment event is created, then reserve event is created. But if the inventory is failed, then inventory failed is created as an event, refund payment is created as an event, and cancel order is created as an event. These are compensation transactions. All of this 2PC is also covered in one of the video, and Saga is also covered in the previous video. So when will you choose what? When you want compensation transactions and local transactions are fine, you will have better availability, loose coupling, works well with microservice, and no global transaction lock is needed. But it does not guarantee you strong consistency with asset semantics. So temporary inconsistency is always there. So what would I choose for what? Usually I would choose Saga for microservices. For tightly controlled systems, I will still have the 2PC possibility. So I would generally prefer Saga in microservice because it preserves the autonomy and availability. I would still consider 2PC only when strong commits across participants are really needed. So Saga trades immediate consistency for availability and compensation logic. What does that mean? So what is the trade-off? If you use Saga, you will have eventual consistency. If you use 2PC, you will have strong consistency. But a cost of what? On the cost of the fact that they will have tightly coupled, and that is against the microservice design pattern. Now, what will you choose? Vertical scalability or horizontal scalability? Vertical scalability is when you increase the RAM, CPU, and horizontal scaling is when you increase the number of ports in the load through the load balancer. So increasing the power of one machine is vertical scalability, while adding more instances is horizontal scalability. Now, vertical scalability has its own advantage. It is simple, no coordination needed, and it is easy and useful for DB. While the disadvantage is hardware is difficult, expensive, eventually hits the ceiling. Eventually, it will hit a ceiling. When it comes to horizontal scaling, it has much higher capacity, better availability, good scaling, and works very well with serverless architecture. But disadvantage, it is have a problem with load balancing. You have to have the session management, you have to have distributed caching, you have to have service discovery and coordination. So I will choose vertical scaling. It is simpler, but it increases But the problem is increases the cost and the physical cost ceiling. While horizontal scaling is adding more instances, provides better scalability and availability, but it introduces a distributed system complexity. For stateless, I would prefer horizontal scaling, while the database may use a combination of vertical scaling, replication, and partitioning. Now, the last and very important question, which will you choose? Blue-green deployment or canary deployment? Both are good deployment strategies, but the risk is different and trade-off is different. Blue-green is when you have two environments. One is a current environment, green is the new environment. So whenever traffic comes to blue, the new deployed service is on green. You test it and switch the users to green. If something goes wrong, you can roll back to blue environment. But the disadvantage is you have two infrastructure. One is for blue, one is for green. And also switching the 100% traffic at once exposes everyone to a bad release. But the advantages is it is fast rollback. You can directly go and switch to blue and you are back to zero, where you have started from. There is a simple switch and it is easy to reason about. When it comes to canary, you release the changes to small percentage first. And you monitor the error rate, CPU latency, and if it is healthy, then you go ahead and increases the blast radiuses. So advantage is much lower blast radius, real production releases, and gradual rollout. Disadvantages is more complicated traffic management, because first you have to manage 90% traffic to 1, then to 70, then to 30, and so on. So old and new version coexist and database compatibility becomes important. So when will you choose what? If I want simple deployment and extreme fast rollback, go for blue-green. If I want gradual risk reduction and production validation, go for canary. So blue-green gives me a clean environment switch while with a very fast rollback, but it requires 2x infrastructure and exposes the entire user base to new version. When it comes to canary, the blast radius is reduced by gradually exposing users to new version, but requires more sophisticated traffic routing and monitoring. For higher production risk changes, I generally prefer canary. For simple production deployments and faster rollbacks, I will go for blue-green deployments.